Organic Chemistry, Lecture 2, Isomers. The first thing we're going to talk about when we talk about isomers are what are called structural isomers. These are also called constitutional isomers. They share the same molecular formula, but they vary extensively with respect to the bond connectivity and the chemical properties. Remember, isomers are compounds that have the same molecular formula, but how they vary is going to depend on their connectivity and everything else. Structural simply states that the molecular formula is the same, and they have very little else in common. Physical properties are properties that don't change the composition of matter. These are in melting point, boiling point, solubility, odor, density, color, etc. Chemical properties, on the other hand, deal with the reactivity of the molecule with other molecules. This results in a change in chemical composition, and these are dictated by the functional groups present in the molecule. Just think of chemical properties as how these behave with others. Stereoisomers. These share the same molecular formula and atomic connectivity, but the connectivity and where these groups are vary in how they are connected and oriented in space. There are conformational isomers, which differ in rotation around a single sigma bond, and configurational isomers, which can be broken and interconverted only by breaking bonds. What's a Newman projection? A Newman projection is a bird's eye view down the backbone of the molecule. What's that going to look like? Well, how about we talk about a couple? So there's multiple conformations we need to go into, the first being gauche. This is when the largest groups are 60 degrees apart. Staggered is similar, except for the orientation of the largest groups. Eclipsed is when the largest groups are 120 degrees apart, and total eclipse is when the largest group are 0 degrees apart. So let's just draw gauche and eclipsed for butane. So if we were to take a bird's eye view down the molecule, we would see something that looks like this. And I'll note this. The unmarked one is going to be a methyl group. Gauche, as it's stated, is when the largest groups are 60 degrees apart. So in this case, the largest groups would be a methane in the back, like so. As you can see, there's 60 degrees of separation between the methyl groups. And eclipsed, as the name would suggest, is when the rotation puts this view into a varied alignment. And total eclipsed is noted like so. What am I looking at, though? Well, if I were to look down the backbone of a molecule, so if I were to have my, for example, the butane I've been using in this example, if I were to look straight down, I would have a view like this. This is one of the ways organic compounds are going to be drawn on the MCAT, so understanding how to read a Newman projection is going to be important. Cyclic conformations. So when we talk about rings, we need to talk about ring strain, because that's going to dictate the stability of the cyclic molecule. There are different types of ring strain. They vary from angle strain, which is referring to how the bond angles deviate from ideal values. Torsional strain, which is when cyclic molecules must assume conformations that have eclipsed or gauche interactions. And non-bonding strains, which are the result of non-adjacent atoms or groups competing for the same space. This will obviously create some clutter. There are some common orientations for these conformations. The ones you'll know and see on the MCAT are going to be chair, boat, and skew boat. So how about I draw a couple of these? Chair conformation, as you remember from your organic chemistry class, looks something like that. This is very favorable. Boat conformation looks something like so. And a skew boat is some combination between the two. You generally see things like hexane drawn like this. However, these bonds all flex and move. If you take out your modeling kit and mess around with it, you can actually bend this into these shapes. That's how they exist in 3D space. Nothing except for benzene, for example, is going to be flat. What is a configurational isomer now? These can only be interconverted by breaking bonds, and there are two categorizations of these: enantiomers or diastereomers. These are both considered optical isomers because they affect the rotation of plane polarized light, so some of them are going to be what's called optically active. Before we go into our discussion of diastereomers and enantiomers, let's talk about chirality and what it means. Chirality is dictated by whether an object's mirror image can be superimposed on the original image. These are based around chiral centers. An object is considered chiral if the mirror image cannot be superimposed, and achiral if the mirror image can. The most classic example that you're going to hear in most classes when discussing chirality are hands. Although your left hand and your right hand are virtually identical, they're mirror images of each other, and without breaking fingers off, you're not going to be able to superimpose them. So if you're ever wondering how to remember this, just remember that your hands are chiral. What's an enantiomer? Enantiomers have opposite configurations at every chiral center. These have the same physical and chemical properties except for optical activity and reactions in chiral environments. What does it mean when I say reactions in chiral environments? Well, some enzymes are built so that they can handle a certain orientation of molecule, but not the other, even though they're virtually identical. So an example of this is if you were trying to shake hands. You could shake someone's hand right hand to right hand, but shaking hands right hand to left hand is going to be a lot harder. When you're looking at active sites in, for example, enzymes, you're going to note that chirality does matter, and that how these molecules fit into that active site are going to be dictated largely by their chirality. We've discussed optical activity earlier in this lecture, but it might be helpful to have a more thorough discussion on the matter. Optical activity refers to the rotation of plane polarized light by a chiral molecule. Note that for something to be optically active, you cannot have a plane of symmetry within the molecule, because that will not polarize light when you put it through. There are two rotations to think about. If a light rotates in a clockwise manner, you give it a positive or a plus notation. Counterclockwise is noted by a negative notation. There is a situation that will come up though, and that is a racemic mixture. This is when both the plus and minus enantiomers are present in equal concentration. This will thus cancel out optical activity, because one will rotate light clockwise and the other counterclockwise, thus eliminating any sort of activity that's observed. What sort of compounds might do this in a reaction? Well, the most classic example is when we talk about nucleophilic addition reactions. SN1 based reactions are generally going to produce racemic mixtures because the enantiomers produced are going to cancel each other out. Let's talk about the second classification. These are diastereomers. These are non-mirror image configurational isomers. They have two or more stereogenic centers and differ at some of them, and they require that diastereomers have multiple chiral centers. These are noted by the R and S notations. When you're talking and classifying diastereomers, you have to note the cis-trans and meso orientations. Cis-trans isomers are specific subtypes where substituent groups are varied around a bond that is immovable. This will generally be a double bond or a triple bond. Cis means they're on the same side, and trans means they're on opposite sides. So for example, if I were to have a double bond, and I were to have both on the same side like so, this would be considered a cis orientation. If they were on opposing sides, however, this would be a trans orientation. In the name, you're going to see cis or trans to note these distinctions, so you'll be able to tell what isomer it is. Meso compounds are simply compounds that have a plane of symmetry within the molecule. They are denoted by the prefix meso during the naming. So, let me draw an example. Let's use tartaric acid. I will draw one orientation of tartaric acid here. So, this one right here, this one is noted as L tartaric acid. And obviously if there's an L, there is an R, but I won't draw it out. R is simply just this flipped. However, tartaric acid can also have a meso orientation, which is noted like so. If it's written like this, and oriented like this, there's a plane of symmetry right across here. So this is noted as meso tartaric acid. You're probably wondering, what am I looking at? Well, if I were to look at a molecule from directly above it and flatten it out onto a 2D surface, that's what I'd be looking at here. So think of it as this chain is staggered. So if I were to actually draw this out in a different orientation, it would look something more like this. So if I were to put this into space, you're going to have something more like this. So if I were to look directly down and flatten it out, then I would have this. So this compound right here would be noted as mesotartaric acid. Now that we've talked about the different types of isomers, let's talk about how we reach our conclusions. And the best way to do this is with a flowchart. So let's say we've got isomers and we're looking at them. The first question we need to ask is, do they have the same connectivity? So, connectivity. If they have the same connectivity, then we call these stereoisomers. If not, then we call these structural isomers, or constitutional, and we stop there. Alright, so we've gotten to stereoisomers. Now, let's go into how to classify this further. Now, the next question we have to ask is, do we need bond breaking to interconvert? Do we need to break bonds? If yes, we're talking about configurational isomers. If no, we're talking about conformational. Alright, let's go into configurational now, because this flowchart continues on. Are they non-superimposable mirror images? So I'll just write mirror image for here, for now. Are the mirror images non-superimposable? If yes, we're talking about enantiomers. If not, we're talking about diastereomers. Now, within diastereomers, do they differ in arrangement around a bond? So the last thing we need to talk about is arrangement around immovable bonds. So arrangement around an immovable bond. If yes, then we have to denote cis or trans orientation. So there it is. there's a flowchart for how to classify isomers. So from the top, we have isomers. Do they have the same connectivity? No, they're structural. If yes, they're stereoisomers. Do they require bond breaking? If not, then they're conformational. If yes, they're configurational. Are they non-superimposable mirror images? If yes, they're enantiomers. If not, they're diastereomers. What about their arrangement around an immovable bond? Is it different? Then you have to identify cis and trans. Now that we've talked about types of isomers, let's go into some configurations. Starting off, what's a configuration? Configuration refers to the spatial arrangement of atoms or groups in the molecule. There are two types, relative and absolute. Relative configuration is in relation to another chiral molecule, so it's a comparison. Absolute, on the other hand, describes the exact spatial arrangement independent of other molecules, and there's different ways to do this. Starting off with the EZ form. This is based around the German words entgegen, opposite, and zusammen, together. And how you arrange them is based on the Kohn-Ingold-Prelog priority rules. This simply states that you assign based on the atomic bond to the double-triple bond. The highest priority goes to the highest atomic number, and ties are broken by looking at other atoms in the group. So, let's do an example here. Let's say I have this compound. How would I classify this? Well, this is 2-chloro-2-pentene. And we have to look at what? We have to look at the groups. So where does this chlorine fit? Well, it's together with this side. So the way it's bent in, if I look at this group and this group, they're facing the same side. So this would be Z, 2-chloro-2-pentene. Now, what would be E? Well, the E form of this would be like so. So as you can see, they're on opposite sides now. So this would be the E form. It's going to take some practice, but once you figure out the Kohn-Ingold-Prelog priority rules, entgegen and zusammen forms should be pretty easy to identify. The next absolute configuration classifier we're going to talk about is R and S forms. These are based around the sequence of groups around a chiral center. Again, you have to use the Kohn-Ingold-Prelog priority rules. So the first thing you have to do is you have to assign priority accordingly. Then you arrange them in space, and then draw a circle from highest priority to lowest priority. The direction that it spins is given as R clockwise or S counterclockwise. Note that the S configuration is because back in the day, if you were left-handed, you were considered sinister. So that's why we use S when we talk about these orientations. Let's draw a couple of these out and assign priorities. It might be helpful to see that. So, first off, I'm going to go ahead and draw the same compound in two different orientations. So, let's draw out one like so. And I'm going to draw the exact same thing, except in a different orientation. So, oh, excuse me, this has to be a wedge. Alright, so let's assign our priorities. Well, highest atomic number states that chlorine has to be number 1. And then from priorities there, the ethane would be priority 2, followed by the methyl group, and lastly the hydrogen. So if we look at the rotation, this is going in the clockwise direction. So this would be R. This, on the other hand, is going in the opposite direction. So again, chlorine has the highest atomic number, the There's a tie, but this is bigger. Then the methyl, and lastly the hydrogen. And if we were to draw a circle, it goes in the counterclockwise direction, therefore sinister. E and Z forms, along with R and S forms, are ways to classify molecules based on their absolute configurations. The last thing we're going to talk about in this lecture are Fischer projections. These are used to denote 3D structures in a 2D image, and they are a combination of horizontal lines, wedges, and dashes. When I mean horizontal lines, it's usually noted as anything that looks straight like this. A wedge is noted like that, and a dash is noted like so. So, if I were to draw out a Fischer projection, for example, we'll use a simple example, methane. I've got a carbon and I have a bunch of hydrogens, so how would I draw this? Well, something like this. So that's one way to draw it. This is simply stating that the hydrogens here are in the plane of the page. The hydrogen is going here, noted by the dash, is going into the plane, and this is going out. So on the plane, into the plane, out of the plane. Knowing how to manipulate Fischer projections and what they mean, and how you can switch these between Newman projections and other forms of drawings are going to be important come test day. As you can see, orientations in space can vary even though the structures are the same. Know how they vary and what they mean, and you're sure to succeed on test day. Join us next time as we talk about bonding.